So, who is familiar with segment routing? Who is familiar with MPLS? Okay, some people are. So, how do we switch slides? Aha. Let me try to switch slides. Yeah. So, the presentation is specifically about segment routing, about the problem of generating the segment list or label stack to steer traffic over the desired path. So, about me, I'm a developer of Traffic Dictator, which is a controller for segment routing. And previously I used to work for ISP and for vendors. This session is mainly for network engineers who deploy, design, operate networks that either use segment routing or plan to deploy segment routing. And the goal is to raise awareness about this problem and show some caveats of how some implementations might not necessarily do what you expect them to do. And also, if there are any protocol developers who build their own SR implementation, I think that also can be useful. So, a bit of recap about what is traffic engineering in general, not specifically touching segment routing. Traffic engineering is steering traffic over a path different than the shortest path. So let's say in this topology, if you want to go from R1 to R7, shortest path will go through R3 and R5. But if you want to steer traffic over different paths, in this case with blue color, we need some extra steps. The regular routing protocol, ISIS or SPF, is not going to steer it this way. So we use what is known as constrained shortest path first, as CSPF. We prune all the non-blue links from this topology, calculate SPF of only blue topology, and then we need somehow steer traffic over there. One way of doing it is with resource reservation protocol, or RSVP. We can signal hop by hop, signal the label switch path, and then steer traffic over this label switch path. With RSVP TE, we need to signal the path before we can forward any traffic, which is not ideal because there are lots of issues with RSVP. It doesn't support load balancing with ECMP. It's not scalable. It's supported not by that many vendors because segment routing is much simpler and there are more vendors, more open source solution of white box vendors are supported. So segment routing solves the same problem in a different way. Instead of signaling paths, it encodes the desired path in the label stack itself. So we can push multiple labels on a packet, and those labels show how to steer traffic. The challenge is how to compute the correct segment list, because if you calculate incorrectly, traffic will be either dropped or forwarded over incorrect paths. If we push too many labels, more than required, we can hit chip limitations or MTU issues. And one advantage of segment routing, but also a caveat, that a lot of implementations don't generate segment lists at all. They only allow you to do static routing, basically. And this is not a bug, it's a feature, because it means those implementations are very basic and they can use a controller, rely on controller to calculate the segment list and dynamically update it when the topology changes. So, naive implementation. We can use just adjacency seed. Adjacency seed, which signifies a link. So, in this case, we can push one label for each link, and then each router will pop one label and traffic will eventually arrive to its destination. The problem with this approach, too many labels will hit hardware limitations. There are some chips that can push only maximum 4 labels, like Qumran. And also you can hit MTU problems. So more advanced approach use prefix seed. So in this case, we can say, okay, first we steer traffic to R8, and then from R8, before R8, this label will be popped, and traffic will go to R7. And this allows to optimize the label stack. It's also possible to use the combination of node seed and adjacency seed. In this case, if we want to steer traffic to R8 first and then use a specific link of blue color to go to R7. We can use a combination of node and adjacency seed. So the algorithm, I put a more detailed blog post explaining the algorithm, but the overall idea is that first we need to calculate the constraint shortest path first, and then we go, as we know the path, we go from the last node to the first node and compare constraint shortest path first with regular non-constraint shortest path first and see if it's the same or different. And if it is the same, we don't need to do anything, we just go to the next node. If it is different, we need to add the relevant node or adjacency segment. There are some caveats with things like segment routing global block, which can be different on different routers with Anycast, with ECMP, and so on. We'll get to some of those. So we have this test topology. And the goal is we'll see how different implementations will solve the problem of steering traffic over the blue path from R1 to R11. So the expectation is that it should go to R5, then R10, and then R11. Why we don't need to put R8 in the list? Because the shortest path from R5 to R10 will go through R8 anyway, so we don't need to add a label for R8. And because R10, because between R10 and R11 we have two links, and we want to steer over a specific one, we want to use adjacency seed. So, and this is the results. I could test my implementation in Traffic Dictator. I could test Cisco and Juniper. I wanted to test some other, I think Nokia, but I couldn't run it in Container Labs, so that's why I couldn't test it. So they all pretty much generate the same segment list, and they're all correct, so everything works as expected. It's kind of the most basic scenario. Now, what we want to introduce global adjacency seed. In the previous slide, we first steer traffic to R10, and then we use adjacency seed to R11, so we use two labels. With global adjacency seed, it's possible to optimize this to just one label. And unlike local adjacency seed, global one is advertised as index, so it's not advertised as MPLS label. So the router or controllers that calculate segment list need to not only recognize, see the global adjacency seed, it can also need to do calculation of adding the index to the segment routing global block. So it needs to distinguish between local and global segments and interpret them correctly. And if implementation does not support global adjacency seed, not a big problem, can just ignore it and use local one. And this is the result of Traffic Dictator. Instead of 3 labels, we have 2 labels, so it's just slight optimization. And this is what we see on Juniper. Juniper doesn't understand the difference between local and global label, and instead it just puts the index as a label, which is not correct, and it will result in traffic being dropped. And Cisco shows this value of maximum 32-bit value, which is obviously not a valid MPLS label, and traffic will be also dropped. So they get confused by global adj seed, which is something to be aware of. Broadcast links. So with ISIS and OSPF, it's possible to have more than 2 routers connected to a network segment, like multiple routers on the LAN connected to a switch. It's not very common in real ISP networks, but what's much more common is to have misconfiguration, because what if you don't configure link as point-to-point, default settings on all routers is broadcast, and what's the difference is that in link state database, they're represented differently than point-to-point. There is a pseudonode LSP, and also adjacency segments are represented differently in different TOV. So let's see what happens with broadcast links. We have this topology, and there are 2 tests. There is one test is steer traffic over yellow links, which includes a broadcast link between R1 and R4. And the other test is the same as previous one. It's go through blue links, but see if the implementation gets confused by a broadcast link being present somewhere else in the network, even though not on the path. So here we see output from traffic dictator and on Juniper. It's interesting that they're different. They're different labels, but they're both correct. Apparently the algorithm Juniper is different from what I implemented, but both give correct, will result in the same traffic steering. Cisco doesn't work with broadcast links, doesn't support it, unfortunately. But what's more interestingly, let's say just having broadcast links, it's not very common because usually it's just result of misconfiguration. But what happened if we are not steering traffic over broadcast links, we are just have a broadcast link somewhere else in the network? The interesting result, Cisco gets confused by it and steers traffic incorrectly. ECMP. So this segment routing, unlike RSVP, the big advantage of segment routing is we can support load balancing over multiple paths. In this case, we go from R1 or R3 using blue links. It will result in load balancing over top and bottom paths. It's a perfectly normal and supported scenario in segment routing, but it has some caveats. One caveat that depending on the hardware chip being used, it can result in more FIP entries being utilized, and sometimes on some chips like Jericho, it has a very limited number of ECMP entries. Another caveat is that if controller is used to calculate policies, depending on the protocol that is used for communication between router and controller, for example, PSEP need to support multipath capability, which has to be negotiated in order to support multiple segment lists. But BGP SRT is supported by default. NKC does optimization of ECMP. Instead of generating multiple segment lists, we can configure the same prefix seed on different routers, which is called Anycast. And it is possible to optimize in some topologies. In some cases, it's possible to optimize from a multiple segment list to just one by using Anycast seed. It is a common use case for Anycast seed as a multi-domain topologies when you have can be ISIS or SPF and border routers that connect different topologies share an Anycast seed. Here is a test topology. I will try to steer traffic from R1 to R11 using either blue or orange. So the expected result is having two segment lists when Anycast seed is not configured, or having just one segment list with Anycast seed when Anycast is configured. This is the result. So the traffic dictator when Anycast seed is not enabled and when it is enabled. In first case, we have two segment lists, and the other just one with Anycast seed. Juniper also generates correct segment lists, but interestingly, it's different from traffic dictator, but it will also work the same way, but it doesn't optimize with Anycast seed. Cisco, I was a bit confused by it because it has this command, Anycast seed inclusion, but I tested in many different scenarios and I couldn't make it work. So if anyone had any luck with segment routing on ISXR, let me know. But yeah, it doesn't support two segment lists, it just uses one. So something to be aware of. And the last point is what if on a router we have multiple prefix seed configured? There must be some deterministic way of choosing which seed are we going to use. In my opinion, the logic should be as follows, that first we should prefer prefix seed with n flag, which is not seed, that doesn't have explicit no, because explicit no can lead to a lot of strange behavior, because segment routing traffic engineering has its own explicit no mechanism. So if we combine segment advertise explicit no and explicit no in SRT, we can either push multiple explicit no labels or push IPv6 explicit no on IPv4 traffic or vice versa. So it's not ideal. So we should prefer not seed without explicit no over prefix seed without explicit no over segments with explicit no. But this is not, this is just my opinion. It's not any kind of industry standard. In reality, every vendor does their own way. So ISXR chooses just a node seed with nflag with the lowest IP and ignores prefix seed without nflag. And Junos always requires prefix seed that equal to the router ID value, and it doesn't even check for nflag. And the interesting consequence of that is that if you use SRM IPv6 segment routing with MPLS, not SRv6, Juniper requires IPv6 router ID, which normally is not required. That's it. So the conclusion that segment routing simplifies a lot of things for network operator, but not necessarily for protocol developers. So there are a lot of caveats related to generating correct segment list. Just reusing CSPF that was used for RSVP is not suitable for segment routing because it doesn't support eCMP, doesn't support Anycast, doesn't support egress peer engineering. So the good segment list generation algorithm should support eCMP and Anycast natively. And if you, even though you're not developing a protocol, but you are deploying, validating segment routing in your network, especially if it's a multi-vendor network, it's a good idea to test these scenarios and watch out for some caveats like eCMP, broadcast link, global watch seed, and so make sure you know how your implementation generates segment lists and its limitations. And that's it. Last point I wanted to make that even so, I did a lot of testing of my implementation, but what I want to do, I'm looking for any master or PhD student who is interested in this technology and wants to mathematically prove that it would work in every topology. Because empirically it works, but I would be interested in having a theoretical proof.